Welcome back to The Explainer. Today we're taking the absolute chaos of the undiscovered elements and transforming it into a brilliant, mathematically logical map of the universe. We're talking about the ultimate cheat sheet of the physical world.
Because, let's be honest, the modern periodic table is so much more than just a random collection of letters and colors hanging on a laboratory wall. It's an elegant, interconnected system that literally dictates how everything around us interacts, bonds, and exists.
So, here is our roadmap for today. The quest for chemical order, Mendeleev and modern law, the engine of periodicity, navigating the blocks, and finally, naming the super heavy elements. Let's get right into it.
But wait, before we have this beautifully neat structure, scientists faced a massive, overwhelming puzzle. Imagine looking at dozens of newly discovered elements with wildly different properties, some explosive, some totally inert, some heavy metals, some invisible gases, and trying to make sense of the whole shebang. It really leads us to ask, how do we bring order to the chaos of the elements in the first place?
Section 1. The Quest for Chemical Order. Early Classifications.
We can actually trace this incredible chronological journey of discovery. It started with Dobereiner's early triads, where the middle element's mass averaged the other two. Then we got Newland's musical octaves, through Meyer's graphical curve, and finally to Mendeleev's absolute breakthrough. It took decades of serious trial and error to get it right.
And speaking of those early brilliant pioneers, here's a quick trivia question for you to rack your brain. Who is widely considered the father of chemistry? If you said Lavoisier, you hit the nail on the head. It really highlights the rich human history behind these chemical discoveries. But you know, it wasn't just him. Countless scientists over the years contributed their own unique puzzle pieces to finally finding a pattern.
Now, what's incredibly fascinating is Lothar Meyer's curve. He decided to plot atomic volume against atomic weight. Rather than just making boring lists, he graphed the data. And suddenly, these striking, visual waves began to appear on the page.
Look at how brilliantly this illustrates the repeating pattern. The physical properties are clearly a periodic function. The strongly electropositive alkali metals sit right up there on the peaks. The alkaline earth metals are precisely on the descent, and the halogens march right up the ascent. A predictable, repeating pattern had finally been visualized for the world to see.
Section 2. Mendeleev and Modern Law. Cracking the code. So Mendeleev initially arranged his elements by atomic weights, right? But that actually created some pretty glaring defects, like anomalous pairs where iodine had a lower mass than tellurium but chemically behaved like it should come after it. It was a scientist named Moseley who completely fixed this by shifting the focus to increasing atomic numbers. That single tweak instantly solved the historical defects.
Which brings us to the ultimate rule of the game. The crucial takeaway is the modern periodic law. Elements are arranged by atomic number, causing those with similar physical and chemical properties to repeat at regular intervals. This right here is the absolute bedrock of modern chemistry.
Section 3. The Engine of Periodicity. Why it repeats.
And this is our grand aha moment. The entire structure of the periodic table is driven by one thing: outer electronic configurations. It is literally all about the electrons. Elements in the same group have the exact same number of valence electrons, which governs exactly how they're going to react with the world around them.
Section 4. Navigating the blocks. The four main blocks. All right, let's dive into the different neighborhoods, starting with the S block on the far left. This is home to the alkali and alkaline earth metals. And here's a pretty amazing real-world fact for you. These elements are largely found right inside of you, regulating your body's biological fluids.
These elements share some seriously fascinating traits. They have low melting points, they're highly electropositive, and they beautifully impart characteristic colors to flames. Think of the brilliant reds and yellows you see exploding in fireworks. Interestingly, though, beryllium is kind of the rebel of the group. It's not a true alkaline earth metal because its oxide can act as both an acid and a base.
Swinging over to the right side of the periodic table, we find the incredibly diverse P block elements. Make no mistake, this is a very different neighborhood entirely.
The P block houses a real mix of metalloids and nonmetals, spanning groups 13 to 18. What I absolutely love about this block is the history baked right into the group names. We have the plinicogens, meaning fertilizer producers, the chalcogens, or ore producers, and familiarly named groups like the halogens, which literally translates to salt producers. The names tell you exactly what they do out in nature.
And right in the middle, bridging the gap, are the D-block elements, famously known as the transition elements. They quite literally act as the structural transition bridge between those highly reactive metals on the left and the super diverse nonmetals on the right.
Section 5. Super heavy elements. Naming rules. Now, naming these massive lab-synthesized elements is basically like using a cheat code. Roots like nil for 0, un for 1, and tri for 3 are simply combined based on the digits of the atomic number. After you stack them up, you just tack on IUM at the end, and you're done.
Let's actually put this into practice right now. Based on those specific rules, what would be the official name of the newly synthesized element with atomic number 103?
It elegantly combines 1, 0, and 3 to form a niltrium. You just snap the linguistic pieces together like Legos. By understanding these underlying rules, from electron configuration all the way down to nomenclature, the periodic table goes from being just a chaotic, confusing poster in a classroom to a beautifully logical map. Leaving us to wonder, what other universal mysteries can you decode now that you can actually read the very building blocks of reality?